Now the next which we have in the chapter is the collision theory. Now what is collision theory? The theory is related to the rate of the reaction, how the reaction takes place. Somewhere it talks about the reaction. So suppose if there is a reaction A plus BC, and after the reaction we got a product AB plus C. So this is the reaction. Now according to, if I am following the collision theory, then collision theory says that the reaction takes place only when the reactant molecules colloid together. That means here we are talking about the collision of the reactant molecule, and that's why the theory is collision theory. So here the reactant molecules should colloid together to form a product. So the first criteria for a theory, that is for a reaction to take place, is the collision of reactant molecule. That is, reactant molecules should colloid. So the first criteria, that collision of reactant molecule. What we observe, suppose this A molecule and this BC molecule is colloiding. After the collision, these two colloid, it form a product. But at the same time, in the same container, there are the certain A and BC collision. Another A and BC molecule colloid, but they do not form product. Means in a container there is an infinite number of these two molecules, so some A molecule and BC molecule on collision form a product, while the sum of them is not forming a product. So question arises that why certain of the molecules are not forming product. Then collision theory says that only the collision is not the criteria for a reaction to take place. There are certain more criteria for a reaction to take place. So the second criteria is that activation energy. Activation energy. Activation energy is the minimum energy which is required for a reactant molecule to form a product, to proceed into the reaction. Now see, during the reaction at least we come to know that there are the certain bonds are, during the reaction some bonds are breaking and some new bonds are forming. So for the breaking of those bonds, certain amount of energy is required. So if the reactant molecules are having that much amount of energy, then only they will form product, otherwise the product formation will not take place. So during the collision, so these on collision form a product, it means these molecules are having activation energy. These molecules are having that minimum amount of energy, but they are not forming a product, means they do not have that much specific amount of energy. Then next, suppose these are the two A and BC molecule. The molecules have activation energy and form product. Have the activation energy as well as they are colloiding and form a product. But at the same time, there is another A and BC molecule. They also have energy. They also have activation energy. Means their energy is also either equal to activation energy or greater than activation energy. But still they do not form product. So now the question arises, if the reactant molecule is having activation energy and also they are colloiding, then why they are not forming a product? Then again the collision theory says that there is a certain more criteria. The third criteria is the orientation of molecules. Orientation of molecules. That is that during a collision, the molecules should be properly oriented. If they are properly oriented, then only product will form, otherwise the product will not form. That orientation means what? See, suppose if I am considering that I have two balls which are made up of, the two balls made up of glass. I am just colloiding both the balls. Both balls after the collision, I want that they should break. So is it like if I am colloiding it is going to be break? Then answer is no. It's not necessary that on collision they will break only. For breaking, whether the balls will break or not, it totally depends upon the force which is applied on the ball. Means I can say there is some specific amount of force is needed for a ball to break after the collision. So like here the force is needed, here the activation energy is required for a reaction to proceed. Now the ball is something like this. On the one side it is a thicker one, little bit. Till here it is thick. On the one side it is a thicker one, while the other side it is a thinner one. So suppose the ball is having that minimum amount of force, the ball is colloided with that minimum amount of force. But during the collision, what happens? Instead of colliding this thinner region, the thicker region, this region of this ball collide with this part of a ball. Do you think the ball will break? Then again answer is no. The ball breaks only if the thinner area collide together. That is during the collision. So here I can say if the thicker part is colliding, it means the balls were not properly oriented. The balls were not properly oriented. That is a part of ball which was expected to be collide, it is not colliding, while the other part is colliding. So here I can say the ball is not properly oriented and hence it doesn't break. So same thing happen in case of molecules also. During a collision, these molecules, whatever we are having, they should be properly oriented. Now proper orientation means what? Now in the reaction I can say that suppose A, B, C. As I said, during the bond form, during the reaction, certain bonds break and certain bonds are formed. So the molecules will be properly oriented if the part of a bond, like suppose here this bond is breaking and this bond is attached. So I can say the proper orientation is that A should collide with the B part of this molecule. If it is colliding with the C, the molecules will not be properly oriented. Now let's see the proper orientation here. Suppose A is colliding with this area. Now let the collision is taking place between these two. A is colliding with the B part, and if A is colliding with the B part, that is the orientation is proper. Why I'm using our orientation is proper? Because this bond is going to be break, a new bond will form between A and B. So proper orientation means the bond which is going to be break, the region which is going to, the bond where it is going to be formed, only that region should collide. So here the reaction will takes place, and I will say we will get A, B plus C. Suppose second possibility, A collides with BC, but now it is something like this. Instead of B part, it collides with the C part. The molecules will not properly oriented because the C is not going to attach with A. The attachment or the bonding which is taking place between B and A. So the collision should take place between B and A. So this molecule is not properly oriented and hence the product will not form. So even if A and BC have the activation energy and they are colliding, but still they are not forming a product because they are not properly oriented. The simpler example I can say the formation of alkyl from the alkyl halide. We had studied, like suppose I am having some alkyl halide. Let iodine is attached to the carbon. These are the 3 hydrogen atoms. I am adding OH minus ion to this. Now if the OH minus ion is attacking from the front side, if they are attacking from the front side, they bounce back, means the product doesn't form. That means that OH minus ion from the front side never form product. So if it is coming from the front side, it will not form product, means the molecules will not properly oriented. But during the same process, see again alkyl halide. If the OH minus ion attacks from the back side, that is from here. If OH minus ion is attacking from the back side, then what happens? During the process, OH minus ion is linking here, and at the same time as the OH minus ion will attach, iodine minus ion will come out, and ultimately this is the proper orientation, and I will get C, H, 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 and OH will finally attach, and iodine is outside. So here I can say this part is called as a transition state. Transition state means where the substance is getting in as well as the one other substituent is getting out. So this is the transition state, reactant, and the finally product. So this is a proper orientation. That means the product will form only if the OH minus ion is attacking from the back side. If it is attacking from the front side, the product will not form. So this is about the collision theory. So according to collision theory, I can say a reaction will take place only if a molecule having an activation energy colloid together with the proper orientation. If all three conditions or the criteria are fulfilled, then only the product will form. Any of the criteria is not fulfilled, the product will not form. So there should be a collision of molecule. The molecule should have energy either equal to activation energy or more than activation energy, and the molecules should be properly oriented. Here also similarly we get the during the collision. In this case also we have a transition state. What happens in transition state? A comes closer to B and C. A is getting closer to B, and at the same time C moves away from A. And finally what happened? This bond forms. This is the final product. This forms and C gets out. So ultimately I can say this is the transition state and this is the product form. Out of the whole reaction, the transition state is highly unstable state. Unstable state, and that means having the highest energy during the reaction. So during the formation, the transition state should form, which always form at a very high energy. Now let us try to understand how the reaction how its energy changes during the process with the help of this graph. So here it is the graph of energy versus reaction. It is how the reaction is proceeding. Now in the case of this is the energy of a reactant. Suppose this is 10 kilojoule here. This is 20 kilojoule, 30 kilojoule, 40, 50, and this is 60 kilojoule. Energy is in kilojoule. So this is the energy of the reactant. The energy of the reactant, so here I can say the energy of the reactant is approximately 20 kilojoule. And this is the energy of product. Let the energy of the product is somewhere 10 kilojoule. Now in this case, in a graph I can say that during the reaction, as you are proceeding, the energy goes on increasing, reaches to the highest value, and again the energy goes on decreasing. This is the energy increases because this is the energy which required for the breaking of a bond. Once the bond breaks, then after the breaking of a bond, the new bonds are forming. The breaking of bond is always endothermic, means they require heat. That's why the energy goes on increasing. And for the formation of a bond, always the exothermic, that is the heat is evolved when the bond is formed. Now this point which is having the highest energy here, that is this point whose value is approximately 60 kilojoule. This point is called as transition state. Transition state, where partially the bonds are broken and partially the new bonds are formed. So here for the previous example, we consider A plus B. The example of the reaction was A plus BC gives AB plus C. So in this, A and BC is a reactant. This is the transition state. Transition state I can say where this is the transition state of the reaction A, B and C, which is having the highest energy in the reaction. Now, so if the reactant, this is the average energy of the reactant. Some reactant molecules are having at this much temperature, some of them are having this much, some of them are having this much, some of them are having this much energy. Some reactant molecules energy is 20, or some of the reactant molecule is having less than 20 kilojoule energy also. Some of them are having 30, 40, 50. So only those reactant molecules get converted into product whose energy is either greater than 60 kilojoule or equal to 60 kilojoule. This is the average energy. We consider the average energy here. This is the transition state. So for a reactant molecule to get converted into a product, how much energy they needed? Then I will say they needed this much energy, that is 60 kilojoule energy to get that transition state. And the energy of this transition state is called as transition energy. This is called transition energy. Now in this case, here I can say this is the energy. So suppose if the reactant energy is 20 kilojoule and if it want to get converted into product, then how much energy is needed? So I will say 60 is the energy which is required. A reactant is having 20 kilojoule energy, that is the needed energy is 40 kilojoule. So that energy which is required for a reactant to get converted into product is called as activation energy. So here this difference is called as activation energy. So I can say that what is activation energy? Then it is a difference of transition energy and the energy of the reactant is called as activation energy. So this is the energy of the reactant and this is the transition energy. So their difference, this difference is called as activation energy. That is, the reactant molecule is having this, require this much amount of energy to get converted into product. Now, in the case of this, here this is the energy of the, so I can say that this is acting as a barrier, this transition energy or the transition state is acting as a barrier between the reactant and product. If the reactant is able to cross this barrier, it will get converted into product. But if it fails to cross this barrier, it will not get converted into product. So that's why it is sometimes also known as a potential energy barrier. That is energy barrier. Now this is the energy of the product which is approximately 10 kilojoule. So this is the difference of the energy. This is nothing but enthalpy of the reaction, that is called as delta H. So delta H, which is nothing but the difference of the product energy and the reactant energy. So if I'm talking about the forward reaction, this is the forward reaction, I can say, where the reactant is giving product. If I'm moving in this direction, this is a forward reaction. But if I'm moving in this direction, this is a backward reaction. If I'm starting from here, this is going to be a forward reaction till there. But if I'm starting from here, that is from product to reactant, then it is going to be a reverse reaction for me. So what is the activation energy for the forward reaction? Then I will say activation energy means I'm starting from here forward to the here. So this is the activation energy for the forward reaction. EA, activation energy for forward reaction. Similarly, what will be the activation energy for the backward reaction? So again, this is the transition state. For a product, suppose if this is acting as a reactant, now I'm talking about the reverse reaction where the product will give reactant. So for a product to get converted into reactant, again it have to cross this barrier. So for a product, how much energy is required to cross this transition state barrier? So I will say product is having 10 kilojoule of energy and how much is needed? 60. So this is the activation energy for reverse reaction. Activation energy for reverse reaction. So here I can say we get a formula then. So activation energy for the forward energy is 40 and activation energy for the reverse from this data I can say 60 minus 10, that is equal to 50, and the difference of these two is 10 and this difference is also 10. So here we got a formula and the formula is delta H is equal to activation energy for forward reaction minus activation energy for reverse reaction. A very important formula we have. Whether the forward reaction activation energy will be high or backward, that is the reverse reaction activation energy will be high, totally depends upon whether the reaction is exothermic or the reaction is endothermic. If the reaction will be exothermic, delta H will be negative, and if it is endothermic, the delta H will be positive. Currently in this case, in this reaction, I can say this reaction is a what, exo or endo, then simply I will say the product energy is 20, the reactant energy is 10. So delta H is what here? The delta H, that is product minus reactant. It is delta H, formula is product minus reactant. That is absorb energy is only 40 joules, 40 kilojoule of energy from 20 to 40. Absorb energy is 40 but emitted energy is 50. So more amount of energy is emitted, that is the reaction is exothermic. So this is an exothermic reaction. So if the reaction is exothermic, we can say from this activation energy for forward is how much? 40. For backward is 50. So if it is exothermic, delta H will be negative. That means this difference is going to be negative. It means for an exothermic reaction here I can say the activation energy of the forward reaction, when I will get the answer as a negative and this term will be bigger, that is activation energy of the reverse reaction is bigger than the activation energy of forward reaction. Now let's see the same graph in a short for the endothermic reaction. Now what happens if the reaction is endothermic? Again, energy in kilojoule versus reaction progress. The graph will be something like this. Now here, this is the energy of the reactant. This is the energy of product. And this is going to be the transition state. And the energy associated with this will be going to be a transition energy. Now in this case, I can say the activation energy is what? This is going to be the activation energy for the reactant. And this is the difference between the product and the reactant energy. That means this is going to be delta H. Now in this case, I can say when the reactant gives this, here the more amount of energy is absorbed while the less amount of energy is evolved. That means the reaction is an endothermic reaction. More amount of heat is absorbed and the very small amount of heat is evolved. So the reaction is endothermic. Delta H, the formula is product minus reactant. If this is 10 kilojoule and this is 20 kilojoule, 30, 40, 50 and 60 and so on. So here I can say delta H, formula for the delta H, it's a product energy, that is 20, minus reactant energy is 10, that is answer is plus 10 I am getting, that is the reaction is endothermic. Now again, if I am talking about the energy of activation energy for the forward and reverse reaction. Forward reaction means where the reactant gives product. So here activation energy for forward means the difference between the reactant energy and transition state energy. So this will be the activation energy for forward reaction. And in this case, if I'm talking about the reverse reaction means where the product is giving reactant. Product is giving reactant means the activation energy will be the difference between the transition energy and the product energy. So EA for the reverse reaction. So here the value says 50 and here the value says only 40. So from this graph, simply I can say that in case of endothermic reaction, the activation energy for the reverse reaction is less than the activation energy for the forward reaction. Let's see with the help of this. If the reaction is endothermic means the delta H is going to be positive. So activation energy for forward minus activation energy for reverse is going to be positive. And if I'm getting when I will get the positive answer when this will be bigger than this, that means activation energy for forward reaction is more than the activation energy for reverse reaction. So the point which the conclusion from the graph is that the difference between the activation energy from the forward and backward reaction, that is the reverse reaction, is delta H. Whether forward reaction's activation energy will be high or backward reaction, that is reverse reaction activation energy will be high, can't be predicted until and unless the reaction's condition, that is exothermicity or endothermicity, is known. If it is given that reaction is exo or endo, we can predict which will be bigger. After this, the transition energy is always having the highest energy, and the energy between the reactant and the transition state is known as activation energy.